So I think we can start. So good morning, everybody. So I would like to welcome you to Open Readings 2023 conference for students of physical sciences and natural sciences. I'm really happy to see you all here in person in Vilnius this year after 2 years of online conference. And I hope that you will enjoy these 4 exciting days in Vilnius, Lithuania. So try to explore it, try to have a good and fun time sharing your findings and spreading the science. So this year we have almost 400 participants from all over the world, and we will have 7 invited speakers, 1 special event, and a social evening. So I'm inviting you to participate in there. And any further information you can find at the registration desk or in our page. So check out the latest news. Also, this conference wouldn't be possible without our sponsors. So a huge thanks to them. And now, without further ado, I want to introduce you to His Magnificence Vilnius University Rector Rimvydas Petrauskas to open our conference. So, thank you.
Thank you very much. So, honorable guests, dear colleagues, organizers, but most of all students and young researchers from all around the world. It's a really great honor for me to address you on this special occasion. I can sincerely claim that Vilnius University is proud to host Open Readings, an international academic platform which gives a voice to so many young intellectual people. These days we talk a lot about the future of democracy, liberal values, and the idea of a global society uniting people, despite their differences. It is conferences like this where we can see that there is common ground for globality. There are places where people can gather and discuss, learn and exchange, share their scientific and intellectual experiences, meet experts and enjoy the uniting purpose of seeking through. In my opinion, such events form the nucleus of modern open academia, and we must make every effort that scientific cooperation events become the basis for more open and fair political management and social relations. When discussing future strategies and goals, countries usually emphasize the importance of young talents and the vitality and intelligence they bring. But it is unfortunately not so often that countries seeking attract young talented researchers create an environment suitable for the growth of these skillful people. Platforms like Open Readings are a rare example of such an environment that provides opportunity for talented young scientists to be heard and to openly discuss their ideas. This demonstrates that if we look for continuous scientific progress, we must create adequate conditions. Let's not only keep our labs open, but our minds and our public discourse too. The conference Open Readings has already become a well-known forum of interdisciplinary sciences, attracting world-class guest speakers and hundreds of students and young researchers from Lithuania and foreign academic institutions. We heard so about 400 is an amazing number. This year, the international geography of the conference, 12 or countries, so is constantly expanding, and as well the numbers of participants. The range of the scientific topics discussed at the conference is very broad, reflecting trends in the development of a modern natural sciences, from astronomy and astrophysics to chemistry and bioinformatics. Even every year, the Open Readings Conference creates an excellent space for early career scientists to get acquainted with current scientific issues, to discuss their research with colleagues and experts from different fields to establish new contacts and start scientific networking, and even to initiate the scientific cooperation. It is especially gratifying to emphasize that for many students, the presentation of their first scientific results at an open readings conference was the beginning of their scientific journey and academic career. They return later to the conference as speakers and experts, inspiring the next generation of young scientists. I believe that the 66th International Scientific Conference for students of physics and natural sciences will become an individual breakthrough for some of you looking for answers, constructive criticism, new perspectives, or simply the confirmation that your research is important and worth all the effort you have put in. I encourage you, our young colleagues, to share your thoughts, expand your networks, and create new friendships. To listen and to reflect on the ideas that might change our understanding of the world. Enjoy these exciting programs, these 4 days, and the opportunity to be part of a global scientific community. And let's celebrate our science together. So I welcome you all and wish you memorable discussions, valuable experiences, and simply good time in Vilnius at our Vilnius University. Thank you very much for your coming. I wish you a good conference.
Thank you to your magnificent rector for such kind words to all of you. And I am Dovydas Banevičius, and it's my great pleasure to chair the first plenary session of this amazing conference. And I would like to introduce the first plenary speaker, Professor Maria Abrahamsson. She received her PhD degree in physical chemistry and started her career at Uppsala University. And then she was a postdoctoral researcher in chemistry at John Hopkins University. And now, Professor Maria Abrahamsson is a professor of physical chemistry and the director of material science area of advance at Chalmers University of Technology in Gothenburg, Sweden. And she will give you a talk about electricity and fuels from the sun. Huge applause to Professor Maria Abrahamsson.
Thank you. Now let's just check that you can hear me all right. Yes? And, oh yeah, here we are. Here we are. So, first of all, it's a great pleasure to be here. It's very nice to be in Lithuania. It's the first time for me, but the most important thing is, of course, to be at this meeting. Because if we learn something from the pandemic, that is that we really need to get together and discuss our science, because science gets better that way. Okay, maybe let's just go back for a second. So I will talk about electricity and fuels from the sun. But what do we mean with that? Well, that means we need to do photochemistry if we should use the sun. So what is photochemistry? If you ask Google, this is what you get. If you ask IUPAC, they tell you that it's the branch of chemistry concerned with the chemical effects of light, for UV to IR. If you go back in the literature, you can find people who claim that photochemistry is the most important science of all the sciences. That, of course, speaks to me. Maybe not everyone agrees. But anyway, I decided that, it's as you probably know, usually you get 15 or 20 minutes for your talk, but now I suddenly have 45 minutes, maybe even 50. So I decided to give a little bit of historical background also into this, because I feel like sometimes it's interesting to understand this as well. Also, and especially since there are young scientists in the audience here, I want to stress this point. We don't always know what our findings are actually going to lead to. Sometimes they might seem a little insignificant, but they may turn out to be very significant later. If you want a good example of that, that is not at all related to photochemistry, it's of course RNA. That was a molecule that seemed to be horrible to study because it goes to pieces as soon as you even try to look at it. And everyone thought that it was just an academic curiosity. And now many of us are vaccinated with COVID-19 vaccines that are based on RNA. And no one could figure out that that would happen when they first studied RNA. So, 1717, the essay Light and Heat, Their Action of Silver, was published by Carl Wilhelm Scheele. And many people would argue that that is maybe the start of modern chemistry, photochemistry, as we know it today. And then you see it's like, it took a few years, and then we come Grotius, and then 1852 Stokes. Some of you have probably heard about the Stokes shift. That's the same Stokes. 1852 also Baer formulated his famous law of absorption. We got the first artificial light source in 1860. The hydrogen spectrum is probably familiar to many of you. That was 1875. And in 1900s, Planck reported that the energy of a monochromatic resonator was not continuous, but was divided into smaller and smaller, discontinuous but unique energy packets. We don't need to go into details here, but Scheele is a good example because his essay there, that was really what paved the way for modern photography. If you go to a photography museum, you see all of these silver gelatine print and whatnot, and that comes from this. And you can follow the line here all the way to the Kodak company, which you probably all have heard of. And interestingly enough, they were super big in the photography world. And then they actually did develop a digital camera, decided that this is never going to fly, and now there are all other companies that are the big companies in photography. So you can do some things right, and then you miss an opportunity, and suddenly you're not leading anymore. We just continue our history a little bit. You start going into the 1900s, you see some names that you probably recognize. Einstein, for example, he did lots of contributions, not only to physics and relativity theory, but also to photochemistry. And many other names that you may recognize. And then 1950, and this I want to spend a little bit of time on, the development of the laser. And this was, again, based on Einstein's prediction of something called stimulated emission. So 1970 is the first paper you can sort of find that relates to this. And then you go along the lines here to develop the laser. And what's important here is that, when the laser was first developed, even one of the inventors said that this is a solution looking for a problem. We have no idea what we should use this for. And today there are definitely laser companies sponsoring these conferences, and we use lasers all the time. That's like, no matter what we do on a normal day, we use lasers. So maybe we had those problems, we just didn't know about them. And this is why I really want to encourage you to, follow your curiosity in your science. Because you might find a solution to something that we don't even know yet is a problem. And if we continue all the way through 1900s, in 1999, the Nobel Prize in Chemistry was awarded to Ahmed Zewail for his studies of the transition states of chemical reactions using femtosecond spectroscopy. And I'm not entirely certain, but light conversion might have had something to do with his success there, because we're one of their competitors. But anyhow, so that's how far we come. And if we try to summarize what come out of all of this, we can say that we have two laws of photochemistry that are sort of the basis for everything we can do with light and chemistry. So first of all, for it to be photochemistry, light must be absorbed. If light is not absorbed, it's not a photochemical reaction. That makes sense. The second law of photochemistry states that for each photon of light absorbed by a chemical system, only one molecule is activated for subsequent reaction. And while I think the first one is completely uncontroversial, the second one, you can maybe discuss a little bit. Depends on what you mean with activated, I guess, as we shall see later in my talk. So anyway, if we look at what happens if a molecule or a material absorbs light, we have some sort of ground state here. We come in with a photon, it's absorbed, and we can have relaxation from this first excited state. And here we can get radiative decay. That's when our compound emits light, or we can have non-radiative decay. And here, of course, it's fairly easy to measure radiative decay. It's fairly hard to measure non-radiative decay. But that's our basis for almost everything we do. We try to look at schemes like that and figure out what's happening, what's going on. And this is just to give you a perspective. Roughly a year ago, I did a Web of Science search just to see what, photochemistry in the title that yielded almost 4,000 results. And if you put it anywhere in the paper, it was 45,000. I can promise you that that has gone up significantly since then. And if you talk about photocatalysis, which is a branch of photochemistry, then there's even more. So, and here are just some examples where you could imagine using photochemistry. Photosynthesis is, of course, one example of photochemistry. So if we then move into the present and photochemistry with sunlight, why do we even want to use sunlight? Why should we care? Well, in 2006, so it's getting a few years ago now, Nate Lewis and Dan Osera published a paper where they claimed and did the calculation that the sun is providing more energy in 1 hour than all of the energy consumed by the world in a year. That's sort of an amazing number. Unfortunately, that is not true anymore. We have to probably go to 2 hours now, actually, because that's how much our energy demand has increased over this short amount of time. So that's another perspective to keep in mind. And especially maybe these days when we have an energy crisis in Europe and whatnot. So it's important also for our scientists to keep the social matters in mind. But the good news is that if we think about the potential of solar energy, there is still more than 99% of all renewable energy resources are in the solar and radiation. Just 1 percentage unit increase in direct conversion efficiency is super powerful and have more potential than all other renewables taken together. So there is still a lot of sunlight out there that we could potentially use for our energy demand. So that's just an important thing to keep in mind. So with that, I was going to go into a little bit of my science and what we do. So basically, we can say that we look at light-matter interactions. And maybe I should go to this slide first. So I will, if I have time, I will tell you 4 different stories of what we do in my lab. So it will be about fundamental studies on long-lived charge separation and multi-electron transfer. It will be spectrum manipulation, so photon up and down conversion, and why that's important. I will tell you a little bit about what we do in photocatalysis, trying to transform CO2 into more high-value chemicals. And if I have time, maybe say a little something about chromophore design and where you can end up by serendipitous findings. But light-matter interactions. And what we usually do is we work with hybrid systems. So we base them on some kind of semiconductor material and also add molecules to that. Why do we do that? Well, it turns out that molecules are super useful because they are easily tunable. You can tune their properties fairly easily. You can get high selectivity with them. So if you want to make a reaction, you can get the desired product instead of a mix of products. That's super useful. However, and especially if you want to work with multi-electron transfer reactions, it turns out that molecules are unstable. Materials are much, much better in that regard. So if you want to store many electrons, for example, a wide bandgap semiconductor is going to be much better than any molecule. We work with some sort of hybrid materials. We have some sort of semiconductor. You probably know that they have a valence band and a conduction band. And in the conduction band, you can store electrons. So what we do, and this is very much inspired by the dye-sensitized solar cell field, is you take semiconductor particles, often we make them into a thin film like this. You can sensitize these with dyes that make them sensitive to visible light. The type of semiconductors we work with typically don't absorb visible light because they're wide bandgap semiconductors. Although I will give an example of a semiconductor that does in the photocatalysis part. So anyway, we sensitize these with some dye that makes it sensitive to visible light. So the dye can absorb light, and in its excited state, it injects an electron into the conduction band. And what we try to do is then, in some cases, we put a catalyst also on this thin film, and we can transfer the electrons through to this catalyst, and the catalyst can do the chemistry we want. That's one possibility. Sometimes we also just use the semiconductor as a substrate to control the orientation and the distance between our molecules. So what you can probably figure out from just looking at these figures is that, of course, there are different reactions going on here. We're moving electrons after the absorption of light. And this, of course, happens with a certain rate. And if we can move them one way, maybe they can go back. And that is, of course, something that we don't want. So we try to study these processes on timescales from femtoseconds to sometimes days and weeks. So it's a large variety in the instrumentation we're using here. Excuse me. And we're trying to figure out both what happens and how we can control this. That is the basics of what we do. So let me start with long-lived charge separation and multi-electron transfer. And why should we care about this? Why is this interesting? Well, most of what we call fuel-forming reactions require multi-electron transfer. So if you want to make hydrogen from water, that takes 2 electrons, or 4, depending on how you count. But it's a multi-electron process. If you want to reduce CO2 to something else, then the CO radical, it takes at least 2 electrons, often more. If you want to, which is another very interesting reaction, transform nitrogen to ammonia. That's a 6-electron reaction. And if you know something about molecules, you know that 6 electrons or 4 or even just 2 is often very hard for a molecule to take care of, and especially if they should hold that extra charge for a long time. So that's why we're looking at this, so very fundamental projects. So as I said, we're combining molecules and materials for stability, but also for tunability and selectivity. So we have two examples here. In this case, we have mixed two semiconductors, and then we also have a dye and a catalyst. The catalyst here is just a model catalyst that could electrochemically reduce the CO2, so we hope that it could also do it photochemically. And the dye is an organic dye that absorbs light, visible light. So we have two approaches here. One quite elaborate. We did tin oxide base when we put TiO2 on top of that on certain spots, sensitized the TiO2 with the dye, put the catalyst here. So that was quite an elaborate approach. And you can see here is just the profile of this. So you can see that we really have a difference. Here is the tin oxide. It's a little thicker in the middle, but quite thin. And then we have the TiO2 on top of that. So this makes it possible for us to have selective dye sensitization and selective attachment of catalyst to this material. So then the question is, of course, does this work? And now we come into transient absorption data. This is all transient absorption. So we take a laser and excite our sample, and then we basically do a normal absorption experiment after that. And then we get time resolution. It's a lot of electronics that goes into this. There are probably people in the audience who are better at electronics than I am, but I know how to use these lasers. And what is the take-home message from this picture is really that, we had, under certain conditions, we see no difference between our different samples here. There's low light intensity. If we go to higher light intensity, we start seeing differences. If we add an additive to this, we also start seeing differences already at low light fluxes. If we go even higher, we see even higher differences. So what does this mean, and what does it tell us? Well, with this technique, transient absorption, and this is on microsecond timescales, so not super fast, we can actually see that here you see, well, we have the laser pulse coming here, and then it's just centered around 0. Nothing is happening. Same here. Here we see a teeny tiny signal, and here we also see a teeny tiny signal. And what that tells us is that we can actually get electrons into our TiO2. They travel through TiO2 to tin oxide and out to the catalyst that is attached there. But unfortunately, we only managed to push one electron that way. And as I said, we need at least two to do any of the reactions we're interested in. So this was encouraging, disappointing. We managed to do conduction band mediated electron transfer, but only one electron. So that is, okay, good, but not exciting. So then my student Elin had just started, and she said, "It's like, okay, this was fun, but do we have to make it so complicated? Is there something else we can do?" So she took TiO2 nanoparticles and made a film out of them, and just said that I'm going to try something simpler. So she just made dye baths where she put both the dye and the catalyst in the same solution. She did this at different ratios, so we kept the dye concentration the same all the time, and then just altered the catalyst concentration. And it turns out that this works beautifully and surprisingly well. Actually, you get very, very reproducible results by doing this. You just take your films, dye them in the solution for a set amount of time, and you get the same ratios all the time. So here the D35 is the dye, the cobalt PPIX, it's the catalyst. This is just our absorption spectra. And we can see that, we get some differences the more of we have of the more relative we have of the catalyst. So, as it turns out, in this case, it was much better to go with the simpler approach. Because here we see, so what we did here in terms of figuring things out, we looked at all of the spectra, we did a lot of electrochemistry here also, to decide, it's like, at what wavelength do we look for the signature of a single reduced catalyst, at what wavelength can we find a doubly reduced catalyst. And then we did these transient absorption measurements, again on microsecond and millisecond timescales. And we see here the different ratios. So we at 438 nanometers, we expect no signal if we have dye only, and negative signal if we have a catalyst that is reduced once or twice. So here we see we have a negative signal in all cases. So that's encouraging. We have a reduced catalyst. We see that they have a different time profile. So we see that it's not the same in all cases. That's also encouraging for us. At 550 nanometers, we expect a positive signal if our catalyst is reduced once, and a change in time, so going to a negative signal if it's reduced twice. So here we see that, okay, we have some sort of buildup of signal and then it decays at the 8:1 ratio, so not so encouraging. In the 15:1 ratio, we see basically the same. We build up a signal and then it starts decaying, and maybe, maybe not. There is a negative sign at the very end here. But when we go to 30:1, we see that, yes, we definitely do have a negative signal. And at 555 nanometers, we expect the same behavior. We should just see slightly larger differences, which we also really do here. So in this case, we could actually show that it's possible, this conduction band-mediated approach, to move at least 2 electrons out to the catalyst, which for at least some applications could be what we need. And this took roughly 0.3 milliseconds to get to this doubly reduced state. Is that fast enough, you might ask? Well, this is, of course, a complication with all of these reactions that you want to do, is that you need to match the rates here. You probably know that absorption is super fast. That's typically femtosecond process. 0.3 milliseconds is significantly slower than that. So this is something that we are putting a lot of effort into, like how can we control these rates and how can we make these materials stable over long periods of time so that we can actually run the reactions we want to run. Moving on. Now I don't actually remember what's next here. I think it's photon up and down conversion. Yes, it is. So what is this? This is a picture of the solar spectrum that also depicts how much light a normal silicon solar cell is actually utilizing. So you see, a solar cell that works with a semiconductor have a band gap. So for that semiconductor to generate a current, of course, you need to be above the threshold value of the band gap. So we will have some photons that are not absorbed at all. That makes sense, right? They can't do anything. They don't have enough energy. Then we have the green ones that are available. We have some that are not used just due to extraction losses. That is hard to get rid of in any sort of system. And then you see that there's a large chunk there that says thermalization, which means that these are photons of enough energy to give us current, but we don't use them efficiently because they have more energy than we actually need. So we see some problems here. We have lots of photons that are not even used in a silicon solar cell at all. and we have some photons that we don't use as well as we could. This is summarized in something called the Shockley-Queisser limit that tells us that roughly 33% is the maximum theoretical efficiency of a silicon solar cell. Is that good or bad, you might ask? Well, think about this. The comparison, a very good comparison here is, how good is a combustion engine that runs on petrol? It's actually not better than that. So, when anyone tells you that solar cells are never going to be efficient enough, they might not be right. We use a lot of other things that are not so efficient either. But of course, we still want to make this better because we have all of these photons, right, that we're not using. So what can we do about this? Well, it turns out that there are two processes that's been known for quite some time that can maybe help us here. One is called photon upconversion for triplet-triplet annihilation. And in this case, you have some sort of sensitizer molecule that can absorb low energy light. This molecule is then fast transformed into its triplet state. We have a triplet excited state. It can transfer its energy through a process called triplet energy transfer to an annihilator molecule, it's called. And if this happens twice, so that we end up with two triplet excited annihilators, if they encounter each other, they can form one singlet excited state and one ground state. So we have two triplet excited molecules that form one excited singlet and one ground state molecule. And this singlet excited state, if you picked your annihilator molecule correctly, can emit a photon with more energy than the photons you came in with. So this process has been known since the 60s. It is, of course, typically we do this in solution. So it's a diffusion control process. Again, we're measuring rate constants. I spend a lot of my time thinking about rate constants, measuring rate constants, fitting rates. And of course, we can define some sort of quantum yield for this. So, of course, this process, the intersystem crossing has to be efficient, the triplet energy transfer has to be efficient, the triplet-triplet annihilation have to be efficient, and the fluorescence have to be efficient. And since this is a product, of course, a low quantum yield for any of these processes are going to take down the quantum yield for this whole process quite a bit. And then we have this F factor also, which from the beginning was considered a spin factor. So this is spin statistics. We're not going into those details, but it also factors in any other losses that doesn't go into any of the other quantum yields here. Anyway, theoretically, the maximum quantum yield of this process is 50% because you need to absorb two photons to get one photon out. So that could, at least in principle, take care of the low energy photons for us and combine them into high energy photons. What do we do with the high energy photons then? Well, there is a process called singlet fission. And in some ways, not all, but in some ways, it's the opposite of what I just went through. So you have two chromophores in your ground state. You photoexcite one of them. And if you have chosen your molecules or materials correctly, and if they are oriented correctly, they can interact in such a way that they form a correlated triplet pair. So you get from one ground state and one singlet excited state molecule to two triplets. They are still coupled together. But if you manage to dissociate and diffuse them apart, you suddenly have two triplet excited states that could, in principle, act as dyes for your solar cell and inject electrons into the semiconductor, and you could get two charge carriers out of one photon absorption event. So here is where I say that maybe you can argue whether the second law of photochemistry is correct or not. Do you activate one molecule, or do you actually activate two? Depends on how you think about it. There is, of course, a lot of energy considerations going into this. Most molecules are not able to do singlet fission. Most molecules are not good triplet annihilator molecules either. So we need to understand a lot about the molecules and materials we're working with here. We need to understand how they interact. The chromophore distance is key here. Also, chromophore orientation is key. And of course, there is an additional challenge, and that is that you can do this in solution, but it's hard to take a solution and incorporate that in a solar cell where you actually want to make electricity, you want to install it on your roofs. Then you don't want organic solvents all over the place, that anything can happen. So incorporating this into some sort of solid state devices is a challenge. So I will tell you two stories here today. The first one is we went back to our beloved semiconductors. Here we have TiO2. We also have zirconium oxide. We took a molecule that is called diphenyl isobenzofuran. That is a known singlet fission molecule. Alter it with a group that could make it bind to the semiconductors, and decided to just study what happens if we do concentration dependence here. And I will not go into the details of all of these transient absorption figures. Now we're doing transient absorption over the femtosecond timescale. But what I think all of you can see is that if we compare this one with this one, they don't look the same. This one doesn't look the same as this one. There is some similarities between these two, but not completely. So this is another thing we do in my group. We spend a lot of time trying to figure out what does these differences mean. And we're doing a quick jump here to the interpretation of all of these data. So what we did is, in the end, we had zirconium oxide, which is a semiconductor that has a very large band gap, so where we don't expect any injection to be able to happen. TiO2, which is used in dye-sensitized solar cells, and also tin oxide, which is also used in some solar cells, which has a lower conduction band energy, which is why it's interesting for us. And we did all of these measurements in two different solvents, acetylnitrile and toluene, so very different polarities. And what we could see is that in the case of toluene and zirconium oxide, we actually had quite efficient singlet fission. Here, however, we don't get any injection. That's not possible with zirconium oxide. So that was sort of proof of principle. Our ID worked, but this is not a system that you can ever make a solar cell of. In acetylnitrile, it turns out that we mostly got to a charge-separated state and got injection instead of singlet fission, although maybe we had a little bit. Here, in the TiO2 case, we only got injection of electrons, only. That was the main process. Almost nothing else happened. When we came to the tin oxide part, it was actually the most successful one. We had direct injection from the singlet state, not what we want, but hard to avoid. But we also have singlet fission, and we do see that we have injection from these triplets. So we have a proof of principle here, even though it's not super efficient. Now, I should say that that molecule, while a good model molecule, it's not great because it's not very stable. And this is, of course, a problem, and especially if you're going to expose something to light. So we decided that we wanted to try something different. So instead of solid state in terms of a semiconductor, can we do solid state or semi-solid state in terms of a gel? And can we then get self-assembly and organization of our molecules in a way that gives us good singlet fission properties, is the question. So we collaborated with Henrik Sundén at Gothenburg University, who does organogels. So have some sort of gelator, we attach a chromophore, in this case pentacene, covalently to this gelator. Hopefully we get self-assembly and a gel. Right, this is the slide I want. So here we have the gelator part. As you can see, there are many places where we can put a chromophore on. So we tried here, 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 and here. These form gels. The other ones did not. This one formed sort of a gel, but not very stable. So that means at least we have some sort of self-assembly. That's good. Then comes the next question: are they close enough for actually, doing anything that we want them to do? And of course, we need to study this very carefully in order to figure out what's going on when you make a new system. We choose pentacene because pentacene is a good singlet fission chromophore and it's well studied. And then Mark, who was a postdoc at the time, he made these molecules. He set out to do the basic characterization and discovered something weird. So in the gels, if we increased the temperature, we got higher emission intensities. If we did this in solution, we increased the temperature, we got lower emission intensities. That's what you would expect, because as you increase the temperature, you increase the abilities for non-radiative decay, so less emission to measure. So this was curious to us. And we tried a few other molecules just to make sure that this was not something weird that was just happening when you put things in gels, because no one had done this before, so we needed to figure that out. And it turns out that tetrazine behaved exactly as we wanted, but we also tried a molecule that is known to do aggregation-induced emission, and there we could actually see that when we put that one in gels, we see the aggregate emission coming out. So that means that we have interaction in the gels. And to make a long story short, actually a very long story, this took us about a year. With a lot of anisotropy measurements, we did NMR, we did more emission studies, and that's another message to all of you young scientists that sometimes you need to go outside your own comfort zone of techniques to be able to solve your problem. So we were able to figure out that all of the emission we see, it originates from species that is very similar to pentacene in solution, but the number of molecules emitting are very, very different, and that differs significantly with temperature. So to us, this means that the pentacene molecules that sit very close to each other in this gel, they are not actually contributing to the emission. Are they doing singlet fission? That's a different story. Here. So again, we're back to transient absorption measurements. And P1, P2, M1, M2, and so on are just the different gels here. And it doesn't really matter which one is which. Again, you see that they don't look the same. So there is not the same process going on in all of these gels. We have significant quenching of the emission in all of them, but the process is different. And we eventually have decided that we think that we maybe have singlet fission in M1. In the other ones, there is some other process going on. Yes, actually, let me skip this. So I will say just a few words on photocatalysis. before I leave for questions. So photocatalysis is catalysis that we run with light. And we are very interested in transforming CO2 to something else. In this case, it's CO. Why is that interesting? Well, CO is a molecule that is used very much in any sort of chemical industry process. So being able to do this in a more circular way would maybe have a huge impact actually on our industry and chemical processing industry. So what we did here when we started this project was that we said, well, we want to do this slightly differently from the beginning. We only want to use elements that are abundant, so carbon, nitrogen, oxygen, hydrogen, and if we need a metal, it's got to be iron. We're not interested in using any other metals. We decided that from the beginning. And started thinking about what we can do here. So we did quantum dots that are based on carbon nitride materials. And they are a semiconducting material, but they're not as wide band gap as TiO2 or tin oxide, so they actually absorb visible light in themselves. So here we don't need a molecular sensitizer, we only have a molecular catalyst, which is attached to the semiconductor particle electrostatically. And to make a long story short here, we do see photocatalytic conversion of CO2 to CO with 96% selectivity. So we make almost no other products here. We have a reasonably high turnover number, 10 to the 6. And we have confirmed by isotope control experiments that this is indeed a photocatalytic process. Something you always should do because there are so many things that could happen here. We do this catalysis with visible light. And currently, I have to say, there are tons of things we don't understand of this interaction. We are happy that we get selectivity, but we don't know why. We see a wavelength dependence in efficiency. We don't know why just yet. So we're trying to figure this out. And here, again, we're doing a lot of spectroscopy because that's what I'm trained to do, of course. We're also moved into calorimetry because that can tell us something about the interactions between these quantum dots and our catalyst. There we found some interesting behavior that we are working on trying to understand in more detail. Sorry, I should go back. So, you know, it's like, this is also, I think, a good message to you that sometimes we have very interesting and very encouraging results. We still need to go back and figure out why does it behave like this? Because if we don't know that, how can we make anything better? Because even though we were super happy with these results, there are certainly more things we need to understand and more things we need to do if we should ever be able to use this. And I think with that, I will skip the chromophore design part to leave room for questions. But I will say just a few things about the future first. You know, today everyone is talking about greenhouse gas effects and whatnot. 1856 is the first paper I found that actually states that the greenhouse effect and greenhouse gases exist. Interestingly enough, that was published by a woman, so she didn't get any credit for this. 5 years later, there was a man who published basically the same thing, and he got all the credit. So, you know, we can all try to do better than that nowadays. And then came a Swedish guy, 1896, and he had his own idea of things. So, you know, he basically confirmed that they have said. And then he also added that maybe it's nice if we can get it a little warmer, which today we know probably not. And with that, I just want to say that maybe we should also try, all of us, to be a little humble. We don't know what our findings will do in the future, good or bad. And then I want to end on this note. In 1912, an Italian photochemist concluded that the sun was the future. I still think it is, but we need to put in some hard work here. And luckily, it's not only me, but a bunch of my students and collaborators, and I'm sure a lot of you in the audience as well. But I really want to point out both my collaborators and all of the guys in the pictures here, because they are the ones who did all of the really hard work. And with that, I say thank you to you for your attention, and I'm happy to take any questions.
Thank you to Professor Maria for this talk. And now the session is open for questions. Sure, Edvinas?
Thank you, Maria, for a very interesting and simple talk. It was a pleasure to hear you. And my question is for you. You suggest that there are two approaches to increase the efficiency of solar cells. One of them is singlet fission for high energy and upconversion for low energy photons. Do you envision that these two approaches can be used in the current solar cells, for example, retrofitted, or any other ways, or is these two approaches just for novel future technologies?
Thanks, that's a very, very good question. I mean, there is actually tries already today to incorporate them with existing solar cell technologies. It hasn't worked super well, I have to say. But I know there are at least dye-sensitized solar cells, which you probably all know that they are not the best ones, but they have their applications in certain areas where they've tried to incorporate upconversion materials and seen that they get better efficiencies. There are some tries with silicon and singlet fission materials where they've seen slightly higher efficiencies, at least. This is, we get into a point where measurement becomes super important, because it is tricky to really characterize these materials and know for sure what's going on. But I would say, I think that we have work to do to be able to incorporate them with current technologies. But I do think it's worthwhile to do both that and to think about how they could be implemented together with novel technologies as well.
Thank you. Any more questions? Don't be shy. I bet there's plenty of things you want to ask.
Everyone wants coffee.
Coffee has to wait. Okay, I have a question myself. On the topic of CO making, I'm interested in the efficiency of the process to make CO from CO2, and is it energetically efficient to do that?
Okay, so another very interesting question and a very good one. So here, of course, it depends on what you mean with energetically efficient. What is the quantum yield for this process? That is one way to address it. And then you could say, well, it's not super high, so there are a lot of photons that we don't use when we try to do this. So in that way, well, maybe not. On the other hand, if we then go back to the very beginning of my talk, just 1% conversion increase will have a huge impact. So maybe we don't need to be that efficient, and it could still be worthwhile. And this is, of course, a discussion we need to have. I don't know if you guys know how efficient photosynthesis is, but it's actually not that efficient. And still, we rely on it for our breathing. So is it a perfect industrial process? No, I don't think so. Is it still worthwhile to see what we can do with it? Yes. that's my take on it.
Thank you. Do you have any questions?
Maria, thank you for our talk. Very interesting. I would like to ask you about maybe photon conversion a little bit more. How do you envision this field, the future perspectives? What will be the first viable industrial application? Or will it be?
Ooh, very interesting question, and a hard one. So, I mean, I think it's very hard to answer that question because what industrial application will happen first depends also to a large extent on random factors like what you can convince an investor to actually put money into, and that might not be science-based. So I don't know if I'm qualified to guess on that part. But I think that we will see upconversion in solar applications for sure within the near future. There's a lot of work going on there. I didn't show you that now, but we are also doing work there and trying to make that go into solid state. And some of my collaborators are doing even more of that than I do. But I think another area where we will actually see upconversion being used is the medical area, because it can be very useful to take low energy photons and convert them into high energy photons by this biomolecular interaction instead of trying to go in with high energy photons that should go through our skin and tissue and whatnot. So there I think we will see that can be very, very useful in diagnostics, for example.
Thank you. Maybe you have questions. Okay, if not, let's thank Professor Maria once again. Thank you so much. And now I was asked to ask you, after this plenary session ends, to go out of this building to take a conference group picture. And then you are all invited to try special conference cake and grab a cup of coffee. Thank you. This session is now finished.